There is a map of the oldest light in the universe, hanging in the offices of some of the most serious cosmologists alive today. It is not a painting. It is not an artist's impression. It is a photograph. The most precise, most detailed, most scientifically consequential photograph ever taken. It shows the universe as it was 380,000 years after the Big Bang, before stars existed, before galaxies formed, before any structure in the cosmos had taken shape. Just a faint, cold wash of radiation stretched across the entire sky, carrying the fingerprint of everything the universe was at the moment it first became transparent to light. Scientists call it the cosmic microwave background. And when you look at it carefully, when you study it the way the people who built careers around it have studied it, it contains something that has no clean explanation. Anomalies, patterns, structures embedded in the oldest light in existence. That point, quietly and insistently, at something that lies beyond the edge of everything we can observe. Something that touched our universe before our universe was old enough to have anything in it. Something that left its mark in the first light, and then retreated beyond the horizon, into a region of space that no telescope will ever reach, and no instrument will ever measure. The evidence is not theoretical. It is not speculative. It is sitting in the data. It has been sitting in the data for decades. And the more carefully scientists look at it, the harder it becomes to explain without invoking something that exists outside the observable universe entirely. This is not a video about what might be out there. This is a video about what the evidence already tells us is out there. And those are two completely different investigations. Let's follow the clues. The first thing you need to understand is what the observable universe actually is. Because most people picture it wrong. They imagine the observable universe as the universe, the whole thing, the totality of existence, with perhaps some vague emptiness beyond the edges. But that picture is incorrect in a way that matters enormously for everything that follows. The observable universe is not defined by the edge of space. It is defined by the speed of light and the age of the cosmos. Light travels at approximately 186,000 miles per second, the fastest anything can move through space. And the universe is approximately 13.8 billion years old. Which means the furthest light we can ever receive is light that has been traveling toward us for 13.8 billion years. Anything further than that, any region of space from which light has not yet had time to reach us, is beyond our observable horizon, not because it doesn't exist, but because the light from it hasn't arrived yet. The observable universe is not the universe. It is a bubble. A sphere of visibility centered on Earth, defined entirely by how long the cosmos has existed and how fast light moves. Beyond that bubble, space continues. The question is not whether anything exists out there. Space almost certainly does not simply stop at our horizon. The question is, what exists out there? What is happening out there right now? And whether any trace of it has already crossed the boundary and entered our bubble. And this is where the investigation begins. Because if something beyond the observable horizon influenced our universe in its earliest moments, if the conditions that produced everything we can see were shaped by regions we can never directly observe, then the evidence of that influence should be visible, encoded, preserved in the oldest structures, the coldest radiation, and the deepest patterns of the cosmos. The cosmic microwave background is where we start. When the universe was approximately 380,000 years old, something happened that cosmologists call recombination. Before this moment, the universe was so hot and dense that photons, particles of light, could not travel freely. They were constantly scattered by the charged particles surrounding them, trapped in a fog of plasma that was essentially opaque. Then, as the universe expanded and cooled to a critical temperature, electrons combined with protons to form neutral hydrogen atoms. The fog cleared. light was suddenly free to travel. And that first light, the photons released at the moment of recombination, has been traveling through the universe ever since. Stretched by cosmic expansion from visible light into microwave radiation, cooled to just 2.7 degrees above absolute zero, arriving at our detectors from every direction simultaneously. That is the cosmic microwave background, the afterglow of the universe's first moment of transparency. A snapshot of the cosmos at 380,000 years old, wrapped around us in every direction, like a sphere of ancient light. And when we map it, when we measure the tiny temperature fluctuations across its surface, the regions that are fractionally hotter and fractionally cooler than the average, we find something extraordinary. The CMB is almost perfectly uniform, almost perfectly smooth. The temperature variations are on the order of 1 part in 100,000, a precision and uniformity so remarkable that it demands an explanation. Here is why it demands one. The observable universe at the time of recombination was already enormous. Regions on opposite sides of the sky. Regions separated by distances so vast that light could not have traveled between them in the time the universe had existed, somehow had the same temperature to within 1 part in 100,000. They had never been in contact. They had never exchanged energy or information. By every rule of physics that existed before 1980, they should have had no reason to be the same temperature at all. And yet, they were. Precisely. Uniformly. Inexplicably. This is called the horizon problem. And for decades, it sat at the center of cosmology as one of the most stubborn and most embarrassing unsolved puzzles in the field. How did regions of the universe that had never communicated end up so precisely coordinated? The answer that emerged, the answer that most cosmologists now accept as the standard model of the early universe, is inflation. And inflation is the first major clue that points unmistakably beyond the observable horizon. Inflation is the theory that in the first fraction of a second after the Big Bang, in a window of time so brief it makes a nanosecond look like an eternity, the universe underwent a period of exponential expansion. Not the gradual expansion we observe today. An expansion so violent and so rapid that a region smaller than a proton grew to a size larger than the observable universe in less time than it takes light to cross an atomic nucleus. This solves the horizon problem elegantly. If everything in the observable universe was once compressed into a region small enough for all of it to be in thermal contact, small enough for heat to equalize across its entire extent, then the uniformity of the CMB makes perfect sense. Everything we can see was once close enough to communicate. Inflation then stretched that tiny uniform region into something incomprehensibly vast. But here is what inflation implies that most explanations gloss over. If our observable universe was inflated from a tiny patch of primordial space, then the space that was inflated was not just our patch. Inflation, by its nature, inflates everything. And the models of inflation that physicists have developed, the models that best match the CMB data, almost universally predict that inflation did not stop cleanly at the boundary of our observable universe. It continued, is continuing, has been continuing for 13.8 billion years and may continue forever. Beyond our observable horizon, space is still inflating, exponentially, producing new regions of space, new pockets of post-inflationary universe, each one potentially as large as or larger than everything we can observe. Our observable universe, all 93 billion light years of it, all 2 trillion galaxies, all the matter and energy and structure that has ever existed within our horizon, is one bubble in an endless, frothing sea of inflating space that extends without limit in every direction. That is not a fringe theory. That is the straightforward implication of the inflationary models that best fit the CMB data we have actually measured. But inflation does something else. something that brings the investigation closer to home. Quantum mechanics tells us that at the smallest scales of reality, at scales far smaller than atoms, far smaller than protons, at the fundamental granularity of spacetime itself, the universe is not smooth. It fluctuates. Particles appear and disappear. Energy rises and falls. Space itself shimmers with quantum uncertainty that cannot be eliminated or avoided. These are called quantum fluctuations, and they are as real and as measurable as anything in physics. During inflation, these quantum fluctuations were stretched. The exponential expansion of space took fluctuations that existed at the quantum scale, at the scale of the very fabric of reality, and amplified them to cosmic scales. A fluctuation that was once smaller than a proton became a region of slightly higher or lower density, stretching across millions of light years. And those density variations, those seeds of structure planted by quantum mechanics during inflation, became everything. Every galaxy, every cluster of galaxies, every filament and void in the large-scale structure of the cosmos traces its origin back to a quantum fluctuation that was stretched to cosmic size during the first fraction of a second of existence. You are made of matter that condensed from a density variation that began as a quantum fluctuation during inflation. The solar system formed in a region that was seeded by the stretching of quantum uncertainty. The large-scale structure of the entire observable universe, the web of filaments and voids that looks at the largest scales, like the neural network of a vast cosmic brain, is the amplified fingerprint of quantum mechanics operating at the dawn of time. And here is the clue that points beyond the horizon. Those quantum fluctuations were not confined to the region that became our observable universe. They existed everywhere that inflation was operating, which means that regions beyond our observable horizon were seeded by the same process, stretched by the same mechanism, and should have produced large-scale structure on the same cosmic web pattern that we observe inside our bubble. The universe beyond our horizon should not be random or structureless. It should be a continuation of the pattern we see. The same cosmic web extending beyond the boundary of our visibility into regions we can never directly observe. We cannot see it, but the physics says it is there. Now here is where the investigation takes its strangest turn, because the CMB, that ancient map of the universe at 380,000 years old, contains anomalies, patterns that should not be there if our observable universe is a self-contained, isolated bubble with nothing beyond its edges influencing what happens inside it. The most studied of these anomalies is called the CMB Cold Spot, a region of the CMB that is significantly colder than the surrounding area, colder than the statistical models of a purely random universe predict it should be. It is large, anomalously, disturbingly large, and it has resisted every conventional explanation that cosmologists have attempted to apply to it. One explanation that has been seriously proposed and seriously studied is that the cold spot is the imprint of a supervoid, an enormous region of space containing far less matter than the cosmic average, through which the ancient CMB light passed on its way to our detectors. As light passes through a void, it loses energy. It arrives slightly cooler than it would have otherwise. A supervoid large enough to produce the cold spot would be one of the largest structures in the observable universe. And while large voids exist, the one required to fully explain the cold spot is larger than anything we have definitively confirmed. But there is another explanation, one that cosmologists discuss in careful language that does not quite conceal how strange the implication is. The cold spot may be the gravitational imprint of a structure that exists beyond our observable horizon. Something so massive, so vast in scale, that its gravitational influence reaches across the boundary of our visibility and leaves a detectable mark in the oldest light we can observe. If that is true, if the cold spot is a shadow cast by something we can never directly see, then the evidence of something beyond our horizon is not theoretical. It is sitting in our data. It has been sitting in our data since the first detailed maps of the CMB were produced. We have been looking at it for decades without fully understanding what we are seeing. There is one more anomaly worth examining, and it is the one that sits most uncomfortably in the standard model of cosmology. When cosmologists map the large-scale motion of galaxies, not just their recession from cosmic expansion, but their peculiar velocities, the motion they have in addition to the expansion of space, they find something unexpected. Large regions of the universe appear to be moving in a coherent direction. Hundreds of millions of light-years of galaxies, all streaming toward the same general region of the sky, with a consistency that goes beyond what local gravitational attractions can explain. This phenomenon has been called dark flow, and if it is real, if this coherent large-scale motion of matter across hundreds of millions of light-years is genuinely what it appears to be, then the most natural explanation is gravitational attraction from a mass concentration beyond the observable horizon. Something so massive that its gravitational pull reaches across the boundary of our visibility and drags billions of galaxies in a coherent direction across hundreds of millions of light-years of space. Dark flow is contested. The evidence is debated. Some analyses find it, and some do not. But the fact that it keeps appearing in the data, the fact that it refuses to go away entirely, no matter how many times it is reanalyzed, means it cannot be dismissed. And if it is real, its implications are extraordinary. It would mean that the observable universe is not gravitationally isolated from what lies beyond it, that the boundary of our visibility is not a wall, that something on the other side is already pulling on everything inside, already here, already influencing, already leaving its mark on the motion of matter across scales that dwarf anything we can comprehend. If these are the questions that pull you toward the edge of everything human knowledge can reach, if following evidence into territory where the answers get stranger the further you go is the kind of journey you want to keep taking, then Cosmora is where that journey lives. Subscribe and stay with us. The clues go deeper than this. But before we close, here's what the evidence actually says when you read all of it together. The CMB is too uniform to have been produced by a universe that stops at our horizon. Inflation solves that problem, but only by implying a universe incomprehensibly larger than anything we can observe. The quantum fluctuations that seeded every structure we can see were generated by a process that operated everywhere, not just inside our bubble. The cold spot in the CMB may be a shadow cast by something beyond our visibility, and the large-scale motion of galaxies may be the gravitational signature of a mass concentration that exists in a region of space from which no light will ever reach us. None of these clues are definitive on their own. Science is careful. The language is measured. The conclusions are qualified. But when you lay them side by side, when you follow each thread of evidence to where it points, they all point in the same direction. Beyond the edge of everything we can see, something exists. Something that influenced our universe before our universe had stars. Something whose gravitational reach may already be shaping the motion of matter inside our observable horizon. Something that left its fingerprint in the oldest light in existence, and then retreated beyond a boundary that physics will never allow us to cross. We cannot see it. We cannot measure it directly. We cannot send a signal to it or receive one in return. But we can read what it left behind. And what it left behind is a set of clues, so consistent, so persistent, and so carefully embedded in the fabric of our observable universe that the most uncomfortable conclusion is not that something exists beyond our horizon. It is that something beyond our horizon already knows we are here. And unlike us, it can see the whole picture